So the Cauchy-Schwarz inequality is an inequality that is respected by all inner products. Okay? For the dot product, it simply says this. Okay? A dot B in absolute value is less than or equal to the product of the norm of A and the norm of B. Okay? This is not a very impressive inequality for the standard dot product, because we know that A dot B is the norm of A times the norm of B times the cosine of the angle between them. So all the Cauchy-Schwarz inequality would say for the standard inner product is that the absolute value of cosine theta is less than or equal to 1. Not terribly impressive. All right? However, this inequality can be generalized to work with every inner product. Let's see how. So, given X and Y in an inner product space, an arbitrary inner product space, I want to consider square of the norm of X minus ky for some real constant k. All right? This proof can be extended to fully complex numbers. It's just a bit more awkward to prove when I allow everything to be complex. So I'm just going to show you the real version. All right? So, I mean, as always, the square of the norm of X minus ky is just the inner product of X minus ky with itself. Now, we're going to proceed, but only by using the properties defining an inner product, so that we can say that our result is valid for every inner product. All right, so the first thing I'm going to do is this. All right, so what have I used here? Well, I used linearity, right? Linearity is property 1 of an inner product. So certainly, my inner product must satisfy that. Next, I'm going to switch these around. All right? What I used there, of course, was property 2, symmetry. And now, I'm going to use linearity again. All right? And then I'm going to use symmetry again. Just like that. Now, so far, we've only used linearity and symmetry. The third property, positivity, guarantees that this must always be greater than or equal to 0, with equality implying that x minus ay is the 0 vector. All right? Now, let's not let all the symbols distract us. X and y are two vectors in an inner product space. So the norm of x squared is a number. Minus 2 times the product of x with y is a number. The norm of y squared is a number. So this quantity on the left-hand side of the inequality is a quadratic function of k. That's what it is. All right? It's a quadratic function of k with a positive coefficient of k squared. All right? So if I was to graph this polynomial as a function of k, it must either look like this, or like this. Right? And these situations would be characterized by red, distinct real roots, orange, single degenerate real root, green, complex conjugate non-real roots. All right? Now, this always has to be greater than or equal to 0 by the definition of an inner product. So red is inappropriate. Red cannot be the case. Because if red was the case, then that would mean that these values of k cause this to be negative. And it can't be negative. Because the inner product was an inner product. So that means that the roots of this polynomial must either be non-real or they must be the same. Of course, that translates into a condition on the discriminant of this polynomial. The discriminant of this polynomial must be negative, or at best, it could be equal to 0. So let's see what that tells us. The discriminant, b squared minus 4ac less than or equal to 0. So if I rearrange it, I'll find or on taking the square root and the absolute value, all right? Now, not only do we have this, we also know that equality implies that there's a value of k that causes the norm of x minus ky to be 0, which again by the definition of the inner product, implies x minus ky equals 0. And that would imply that xy is a linearly dependent set. All right, so if x and y are linearly independent, then this inequality is strict. It must be strictly less than. This inequality is satisfied for every inner product, even the integral ones we've been using in polynomial spaces. It becomes a very, very useful tool for exploring the relationships between integrals.